a fixed parameter almost. But when you come to university, the water has got various parameters, like the temperature of the water plays a role because it affects the viscosity of the water and things like that. And if you understand it and you are interested, then it's stuff that you say, wow, yeah, this is logic. Obviously, if water is very hot or very cold, the flow properties are different. So it makes sense to me. Whereby if you are not interested and it doesn't make sense, then it's sort of, what's all of this additional stuff? I just want to know that the water is flowing. So there's for sure a deeper level of complication, but it's not a it's not complicating it in terms of why do you add these things. It's complicating it in terms of, okay, this makes much more sense because I'm trying to understand the system in much more detail at this stage.
I think if I could grasp those concepts, then it definitely would be more interesting.
Yeah, you often find it that students say at school, especially in physics and chemistry and so on, they've learned some stuff, but it was a very, and no offense, but it was very limited or sort of simplified because you don't have that much background knowledge. So therefore, it's a simplified version. And sometimes that simplified version of an equation or knowledge is almost more difficult to understand because you don't have all the other parameters also included into it. But yeah, that's how life works. So otherwise, we would have been very busy trying to understand everything in detail.
True. You mentioned that civil engineer at the engineering facility that you work on some projects with agricultural engineers.
Yeah. The facility. You say you're in Pretoria, so I assume you have driven past on the N4 past our new facility. Have you seen it?
Yeah, I do think I have.
Okay. So that whole part of the campus has traditionally been our agricultural experimental farm. So there's cattle and chicken and sheep, and they plant stuff there and so on. They are moving some of it now because it gets a bit small, but it's been our agricultural experimental farm. So there's a lot of stuff that the agricultural guys need to know. For instance, we are putting together an environmental monitoring network for them. We devised a sensor box. It's about 15 by 5 by 10 centimeter size. That's got sensors. It's got DPS. It's got CO2, particulate media, humidity. I think it's about 10 or 15 parameters that we monitor with it. We call it Snoop. So we've got currently 4 of these that we place at certain locations on the farm. And I'm awaiting our LoRa network antenna to be placed on our building in the next week or two. And then we will be able to move these sensors around the farm and continuously get data on the environmental conditions where they are. So we are interested in that because we want to know what the effect of traffic on the road is on the environmental conditions next to the road. So when you've got congestion, as the CO levels go up, there's a temperature affected and so on. And as you get further away, what happens? But the agricultural guys obviously also need that information for monitoring how well their stuff is growing and so on. So that's part of it. Then we also have, we've got a couple of drones in our department itself that we do photogrammetry with of the farm. That's what we are busy with, the digital twin currently. And then one of our drones, we've got a LiDAR unit also. So we can do a LiDAR survey. That also goes into the bigger model so that they can actually track and trace plant growth over time by looking at the LiDAR data that we collect for them. So we use the LiDAR for surveying roads and buildings and so on. But I mean, it's the same whether you survey plants or building. It's the same principle. So that's why they are making use of this in terms of the bigger picture over there.
Sure, that's pretty amazing.
We've got some nice cool stuff. You may remember there was a picture that I spoke about the data. 3 yellow things that sat over there. That's actually our smart avocados. We developed smart avocados and tomatoes that's got a number of sensors inside them, as well as GPS that we put on trucks with avocados and tomatoes to monitor what the produce experienced during the trip from the tree all the way to the consumer. And the reason that we are interested in it is that you can make a direct link between the quality of the road, for instance, and the bruising and bumping of your tomatoes and your avocados. I mean, as an example, you can do it for other fruit and vegetables also. So it's not that we only do the infrastructure construction and design. We do a lot about the operations, about how does it affect actually what happens in the field. So although we are not electronic engineers, we do a lot of our sensors ourselves. We put up recently out in Mpumalanga in the Steelpoort area, we put some sensors in tailings dams at a mine over there. And we are constantly monitoring through a Sigfox network what happens over there. So that's a sensor system that we developed. And we've got a similar one. There's a bridge in Tromsburg in Free State over the N1 bridge that we instrumented 5 years ago with about 550 sensors. And that data is still, up until today, every 15 minutes of every day, it logs all the data, it looks at the temperatures and the changes in the bridge structure, and it sends that data through to us over here. And we use that for various studies and so on. So there's a lot of the sensor technology that we incorporate into the civil engineering part, where we develop them, we use them, and it's a major part of what we do these days.
Wow. I didn't realize how much there was. Sorry.
Sorry, go on.
I didn't realize how much there was in civil engineering. That's really impressive.
Yeah, it's really changing. I mean, when I studied 30, 40 years ago, it was really focusing a lot just on the design and the construction part. But over the years, it developed a lot. The student that actually did the smart avo and tomato for us, he initially developed, you may know that rock on which a railway sits, that large rock that you see, we call it railway ballast. And that's big. That's about sort of the size of my hand. I thought I've got one here, but I don't have one. And he originally developed a smart ballast. So that without any wires or so on, we 3D printed the ballast, put the computer and everything on the inside, and put that on a real railway line to measure as the train gets past, how does the ballast move. And the reason why that is important is you always need to go and sort out why do we need to know it as civil engineers, is that if you've got two pieces of ballast and the train goes past, they sort of move relative to each other. And that starts to deteriorate them, and that starts to affect the way that they work. So that's a major part of what we do over there. We also do a lot of our own 3D printing. This is part where we help some of the other guys. This is part of a brain. It's for the neurosciences colleague that I've got over there. He's a neuro surgeon, and they wanted to check various features that they can sort of study. So they gave us a CT scan of a brain, and we print it, and it's a flexible type of, you can see it's more flexible type of filament. So we do that. And it's nice to combine this stuff because the guys in chemical engineering, they are developing new types of filament, for instance. So you can look at different properties of filament for 3D printers and see how do you do different stuff with that. We look forward to see you guys here. And we will take details and everything on the website. So if you've got more questions or so on, you are really welcome to just drop an email, and then we can assist in responding and answering and making sure that you know what the nice features is that's available in civil engineering.
Okay.
Sounds perfect. I think we've got another 5 minutes or so. I'm trying to see my schedule over here. If there's more questions or so on. Yeah, they'll keep it open for a few more minutes. But yeah, as I said, please don't hesitate if you do have questions afterwards, so on. You're really welcome to contact and ask. If it's more the admissions and the administrative stuff and so on, we forward you to Mrs. Powell also, who covers that. But if it's more on the technical side and stuff, then you're welcome, and we can help.
Thank you so much.
Am I right?
It's a real pleasure.
So, am I
Yes.
right in saying that a big part of this field is doing research?
Well, it depends on what you're doing. A lot, obviously, with my background, I've been doing research for many years, but I've got colleagues that physically just design buildings or roads on a day-to-day basis. So they are not involved in much new research. They use the latest techniques and so on, but they do the design, and they will, for instance, determine, as I showed you, that final year project that our guys are currently busy. They will need to determine how many vehicles need to use a road, what type of materials are available, and they do a design for that. Then I've got colleagues that are the contractors. So in the contractors, you've got the guys that physically build the facility, the building, the road, or the dam, but you've also got engineers in the contractors that physically take the plans of the consultants, interpret them, and then make sure that whatever is being constructed is actually the real thing, and it's correct stuff that's being constructed. So it depends on what you're interested in. If you want to do field work and so on, construction, very nice. If you want to be more in the office, consulting, quite possible. And if you are interested in new stuff, the research field is big. There's a lot of stuff that we are busy with in terms of research, and it stays novel. I mean, currently we are looking, for instance, at nano-type stabilization for soils, where we change the properties of soils using various types of nanosalines. And that's getting back to your initial question about the chemistry. If you don't understand the chemistry, obviously you won't be able to do that. But once you understand the chemistry and you know what bonds to what in terms of your soil and your modifier and so on, then you start to change the properties of the materials that you're working with significantly.
Sure. I must admit, I do really want to do civil engineering as a career.
Yes.
But can I follow up in eco-engineering? Does it connect?
Eco, like in what type of eco-engineering? What do you see as eco-engineering?
Like finding greener sources of energy and constructing homes and buildings in a more eco-friendly manner.
For sure. The basic degree that you do is still civil engineering, because that's where you learn about materials and about construction. Yes. In that specific example, because if you don't understand the principles of a structure and how the loads on the structure affects the strength requirements for the materials, then it doesn't help much to try and develop more eco-friendly materials, but maybe they are so weak the whole building will fall down. And in the same way, we are working a lot on concrete materials, whereby it may be difficult for you to understand it like this, but it's standard concrete that's got a strength of, let's say, 40, 50 megapascal. We are manufacturing concrete in our laboratory that's got a strength of 150 to 200 megapascal, for instance. So, but it changes the properties of that concrete. We have manufactured previously concretes in our laboratory that's totally flexible. And it's only once you understand the requirements of the building and the potential properties of the material that you can then say, okay, but let's see how to do something more eco-friendly. Can I use this type of material, or let me design and develop a totally new material that will be more eco-friendly, that will be strong enough, that will be durable enough? Because most of these things, there's not only one parameter that's important. So if you look at the material, more eco-friendly material, you want to make sure that it's strong enough, but you also want to make sure that it's durable enough. It must, the building must stand for long enough. You must also make sure that whatever you add to this new material is not toxic, because a lot of your stuff that you can enhance a material with or make a more eco-friendly material is actually toxic either to humans or to plants or animals. So you need to look at that part also. And then quite an important part these days is to look at what's the recyclability of that material once it gets to the end of its life. So if you build a house, for instance, and after 30, 40 years you want to add on to the house, or you want to break it down and build a new house, what can you do with that material? Is it materials that you can reuse and recycle, or is it a material that you just have to discard off because you cannot reuse it? So that's why your basic training will start in the civil engineering to understand the concepts, and then from there onwards, obviously, the field is very open.
That makes sense. That makes sense.
Sir, you also spoke in your presentation about more like this big part of civil engineering that consisted of management. How big is management in civil engineering?
It can become quite big. If you look at most of your companies where, let's start on the one part where infrastructure is being managed. So I've got a colleague that studied with me, and he started a project management company. So what they are actually doing is they don't design or build anything themselves. But like our new building, they were the project managers for that building, which meant they managed the design team and the construction team and the material suppliers. And they made sure that all of them actually, together with the architect, together with the quantity surveyor, follow the right steps, do the right job, and get the building done. That's one part of project management where civil engineers do quite a good job, because you understand the technical requirements and therefore you know what who needs to be doing. But there's also a lot of management where civil engineers are totally out of the infrastructure area. I've got again colleagues that studied with me that's, for instance, working in financial companies, where they've done some additional postgraduate financial studies also, but the whole idea of how do you manage big infrastructure and projects, that is a very good basis for basic management later on in your life.
Okay, thank you.
And that's why I say you can, with a civil engineering background, like with many of the other engineering backgrounds and so on, but you can do the dirty work and be out in the field and really dust and construct stuff, or you can have a much, let's call it cleaner, more civilized office type of work environment where you are not really involved with the construction stuff, but either just the management of projects or the management of infrastructure or something totally more in an MBA type of area.
Okay. Thank you.
Pleasure.
So how does the geotechnical side of civil engineering work?
Okay, the geotechnical side, that's the guys working with soils. So they will tell you, and they are quite correct with it, that everything that you construct must stand on the earth in some way. So whether it's a bridge or a pipeline or a road or a building, it needs to stand on soil. And what the geotech guys is doing a lot is to evaluate and test and investigate the properties of the soils on which you are going to found your building or your road. And then look at, if you want to build a new structure, for instance, what type of foundations do you need? How strong must they be? How big must they be? For instance, again, quite interestingly, our new building, the soil conditions differs on the eastern and the western side of that building. And the geotech guys are the ones that dug the holes initially, tested the material, looked at how deep it goes before you get to rock. And then based on that knowledge, they developed a foundation plan for the whole building, so that you make sure that in some areas of the building, you've got a different type of foundation than in other areas, because the whole building must in the end be stable and level. So that's one area where the geotech guys are busy. Another major part where our geotech people are busy with is with tailings dams at mines. So all the stuff that they take out of the mine, they take the ore out, they take the minerals out, and those big mountains of material that you see next to the mines, that's actually what's called tailings dams. So that's the rock that gets left out afterwards. Now, the whole design and the management of those tailings dams is a very, very detailed science, because you've basically pumped mud into that dam, and then you depend on the rate at which the water evaporates for it to become a solid dam. So it's not a dam with sort of a lot of water on the inside, it's basically a mud dam. And if those things are not well designed, you can get very bad disasters. In 1994, we had one in the Free State at Maryspruit that actually collapsed. And there was quite a lot of lives lost in the town next door. Last year, if you go and search a bit in Brazil, there were two major tailings dams that failed. And again, it had severe effects in the downstream towns and so on, because essentially you've got this flood of mud that just sort of start to run down. So if you search for Brazil tailings dam failure 2019, you should see some of it. There are actually really interesting videos showing this flood of mud coming down. So that's another part that our geotech guys are doing a lot of work in. And linking back to the sensors again, we've developed some what you call soil suction sensors that we actually install in those dams, and they are used to monitor the amount of water that's in that mud as it solidifies over time. So recently, about a month ago, we installed some of these sensors in a tailings dam in Mpumalanga, and we are now tracking that data on a daily basis to see how the material dries out. And in the laboratory, we build models where we then evaluate the rate at which that material dries out and how much stronger the material gets over time. Because that's ultimately what we want to know. We want to know, is it strong enough to actually keep its shape as a dam? So that's a major part where the geotechnical guys are also working on.
That is impressive. There's so many different problems you have to focus on in a single project. How do you separate them all and make the whole project come together?
That's a very important observation that you make. If it's a smaller project, obviously it's relatively okay. You are trained as a civil engineer, you know something about the soil and the structure and the water, and then it's relatively easy. But in any medium to large size project, you've got a team of people that works together. And the team knows everybody. Everybody knows more of their specialist area than the other guys, but everybody knows a bit about the other guys as well. So, for instance, when we had our construction of engineering 4.0, we had the project managers. They basically just made sure that you've got a program, everybody keeps to the program, everybody talks to each other, and so on. Then we had a quantity surveyor. They were just responsible to make sure that, listen, we need 50 tons of steel of this type. It's going to cost so much. It must be delivered on this day and this day and this day. Then we had the architects who designed the whole facility and said what it must look like. Then you had a structural engineer who's a civil engineer that specialized in structures, that said, in order to have this building and to make sure that it's strong enough, we have to have columns of this size, and the roof must look like this, and so on. So that's what they focus on. Then we had geotechnical engineers, and they said, okay, if you want to put that building with that mass and that design onto the soil, you need this type of foundation. Then we had what we call the wet services engineers, which is basically the civil guys that looks after the supply of fresh water to the facility. So where does your fresh water comes in? How is it distributed through this whole building? But also those are the sewage guys, because the management of sewage is a major part of civil engineering. And obviously you need to take it away from the building and link up to your municipal sewage lines, and how do you make sure that that flow happens? So those guys focuses on that. Then we had some road engineers on the project. They looked at the parking areas, at the access roads. Is that strong enough? We also had electrical engineers on, because we need to make sure that we've got electricity everywhere. We've got lights running throughout the building. We had some electronic engineers. They looked at the IT networks and the Wi-Fi networks and everything in the building. We had a mechanical engineer that is responsible for the whole air conditioning system in the building, because we've got a large open area where you've got some requirements for air, but then we've got very dedicated rooms for our concrete testing where, for instance, we can set the humidity up to 99% humidity and 25 to 30 degrees Celsius temperature. Now, it sounds just like numbers. I've been in there a few times the last week or two, three. It feels like middle of December in Durban during a heat wave. You are inside that room for 5 minutes and you have to get out. But that whole environment now needs to be created because we are curing some of our concrete samples there and so on. So the mechanical engineer needs to design that it only happens in that part of the building. And that's done together with these civil materials guys that says, okay, if you want to do that in this room, you have to have walls that are this thick, constructed of this type of material to prevent everything else also getting hot and so on. So you need this multidisciplinary team to actually work together. And as I said, everybody knows something about the other guy's work, so that it's not that you're totally ignorant about it. You must understand what they are doing, but everybody needs to focus on their part. And that's the easiest way to get a big project like that working. And that's whether it's a building, whether it's a big road, whether it's a dam that you are building or so on, that you always work in this multidisciplinary type of teams. We even had some history people on our team because we've got an old monument that we had to move. And it was a case of get history people in. They need to come and tell us what can be done, what may be done, what may we not do, and so on. So yeah, multidisciplinary for sure.
Thanks.
It's a pleasure. It's good to have the discussion about it, because I think the problem is often, especially if you are still at school, one has got this idea that if I become this engineer, I will know everything and I will have to do everything. And yes, there are smaller projects where one is in that type of situation, but it's mostly as you start up the big stuff, you realize this is a team effort.
Yeah.
Any other questions?
So I noticed throughout the day that many of the different types of engineering, in some aspects, they sort of do the same thing sometimes. Where I
Yeah.
can't think of any examples.
Take the transportation as one. The industrial engineering, Prof. Hubert spoke about that. I spoke about that. Mechanical spoke about the vehicles, and electronic, they spoke about the management of the traffic. That can be example, yes.
Yeah. So when you have a big project, like you were saying, how do you know which engineering should be what? Like, where does one end and the other start?
It's a very grey area very often. In terms of the engineering council, all engineers need to be registered with the engineering council, and after you've got a certain amount of experience, you register as a professional engineer. And as a registered professional engineer, one of the things that you actually agree to is that you will only work in areas that you've got the capacity and the experience and the specialization on. So to give you a very personal example, I'm a civil engineer by training, so I've done structures and water and geotech and roads and everything, but I specialized in road. So if you ask me today to design a building, I obviously have got the sort of the background and so on, and I know the basics, and I can pick up my books again and go and make sure about it, but it's really not my specialization. So if I'm sitting on a team and people say, oh, you're a civil engineer, can you help us with the structure? It's sort of my ethical responsibility to say, guys, yeah, I am a structural engineer, I am a civil engineer, but I'm not a structural engineer. Get my colleague that actually specializes in that. He will be able to make, or she, a correct decision on the structure itself. I can help you with the road, with the materials for the road, with all of that. For sure, I've got the experience in that, but I cannot really assist you with that. And you will find that in the engineering industry, and again, it's not only the civil, it's all of the other guys also, companies and people in companies develop areas of specialization. So you will know that if you put your project team together, people will normally tender to be part of that project team, and you will then evaluate what they've done before, and based on that decide what is the best team to put together for this specific project that you are working on. So you may even get, like with Prof. Hubert that spoke about the industrial engineering and some of the transportation work, you may get them sometimes on a transportation project, even though they are not civil engineers, they are industrial engineers. Or you can get some of my colleagues working on a project with them where they need a very specific type of expertise. I, for instance, have got colleagues that worked with the materials and metallurgical engineers in terms of the welding science, where our guys look at the structure, how do you build a steel structure, what are the stresses and strains and so on, and the metallurgical guys look at the chemistry and the metallurgy of the metals itself before and after you welded it. So that's something that you build up over time.
Okay, thank you.
Pleasure. And I think the important thing to realize is all engineering is based on maths, chemistry, and physics. And what we actually do during the process, 500 years ago, when our amount of knowledge about stuff was just that much, you could have a person that knows enough about everything to do it all. But over time, the fields developed so much that it just becomes too much to know enough about to do ethically a good job of what you're doing. I mean, if I want to be ridiculous about it, I know enough about electricity based on the stuff that I've done at university and so on to help myself in terms of an electric network, and I can look at the electricity network in my new building and I can understand it, but I can really not with a clear conscience say I can design it and sign off and say this is the best electrical network design for this facility. And that's where the difference comes in.
So you mentioned the becoming a professional engineer and signing up with the engineering council. Does
Yeah.
that come only after university?
Yes. Yeah, the process basically works like this. You do your 4-year degree at any of the universities in South Africa. Now, again, there's a bit of background. UP, WITS, UCT, Stellenbosch, UJ, and UKZN, that's from a civil engineering viewpoint. All of them provide you with a engineering degree, 4-year engineering degree. If you go to TUT or Kaput in the Western Cape or some of the other universities of technology, when I was younger, we called them technicons, and I know some people still know them by technicons. You can also do engineering training over there, but there you are trained as a technologist. And then once you've got your degree, it's expected that you do at least about 3 years of engineering work. And through that engineering work, you really pick up the practical expertise and understanding and so on. And then after about 3 years of work, you apply with the Engineering Council of South Africa, EXA. You apply to be registered as a professional engineer. And they look at your work record up until that point. And if you've got enough exposure to the various aspects of your engineering field, then they allow you to register as a professional engineer. And the reason why that is important, according to law, if you design a facility in terms of the civil engineers, the mining guys and the electric and all of them has got this similar system. But if I design a road or a building, then I sign off on that design, that it is my work. I'm competent to do that design, and I say this is a safe and economical design. And for the rest of the life of that building, that's the guarantee that whoever has got that it's hopefully a safe building. So you will always see if a building falls down or a bridge falls down or something like that, that EXA is then getting involved, and you can criminally keep the engineer liable that signed off on that design if they did not do a good job. Now, obviously, there's a good investigation always to make sure, listen, is it the engineer that didn't do a good job or the contractor that didn't do a good job, or is it just a force of nature that sort of something happened outside of the design and therefore something happened. But the fact that you registered with EXA provides you with that ability to sign off on your own designs. If you are a technologist, you can also register with EXA, but then you register as a professional technologist, which means that there's different rules. You cannot design stuff on your own and sign off on that. It's only if you're a professional engineer that you can do that. So that's where the whole EXA thing comes in. So typically, your studies will be your 4-year studies, and then roughly 3-4 years after that is when most civil engineers then have got enough experience to actually register as a professional engineer. It's similar to what the doctors do almost. If you study medics, you do, I think it's 5 years MBCHB, and after that you are not allowed to work as a doctor on your own immediately. You must first do your hospital year, and part of that hospital year is your exposure to different disciplines and so on, and then you do a final exam after that, and only then you are a medical doctor that can actually practice on your own. And that's the same with the engineers. The chartered accountant, same story. You do a BCom accountancy, then you do an honors degree in that, then you work for a year or two, then you write your chartered accountancy exam, and only then you are a chartered accountant. So the difference between an engineer and a professional engineer is almost the same, and I know it's not exactly the same, but let's say between an accountant and a chartered accountant. A chartered accountant says you are professionally registered and accepted to be professional in this area. Same with engineers, same with the medical guys and so on.
So if I've signed off on a building that I've constructed, if something were to happen to that building, am I held to come in back and help fix it?
Well, you can come and help and fix it, but you can also go to jail if you stuffed up in the first place. So it's a big responsibility. They can send you to jail if it's shown in the investigation that you did a bad, inadequate design, or you missed stuff and so on. The law allows you to go to jail for that. But fortunately, that doesn't happen often because people realize, listen, this is serious. And we always try to tell the people, I do not want to say it too much in the presentation, but as a civil engineer, you have to realize you are working with people's lives. You've heard about 2 weeks ago when the shopping center that they are constructing here in Pretoria, when the floor fell down. It was about 2 weeks ago, Jacaranda.
I don't think I heard about it.
You can check Jacaranda Center in Rietfontein. They were pumping concrete on the floor, and the floor fell down during construction, and people died. And obviously, we have to wait for the details on what happened, but most of my colleagues are under the suspicion that the support for that floor when they pumped the concrete was not adequate enough. And as a civil engineer, you're the guy that have to design the temporary support while that is being done. The same with, they had 2 or 3 buildings in Durban falling down recently. They had a big bridge accident, what was that, about 5 or 6 years ago on the M1, where a temporary bridge fell down. And the investigation showed that the engineers in that case took a few shortcuts. So they are in for trouble. And the issue is really, I mean, if a building or a bridge fails, people can physically die. And I know the electronic guys don't sort of like it if I say it like this, but if your phone breaks today or it dies, it's not really the end of the world. I mean, yeah, you are annoyed, you paid for the phone is not working, you have to get another phone, but you are not going to die because your phone broke. But if you are sitting in a building and the foundation of the building was designed inadequately and it falls down, then it's not like a phone that you just go and buy a new phone.
What you've just said just gave this whole career more responsibility in terms that you are playing with people's lives and like you just need to build your buildings safe.
Yeah. I mean, the next time, what I always do when we've got you guys on campus for the EBIT week or so, and we sit in one of our lecture rooms, and I ask everybody, listen, when you walked into this lecture room, did you think for a moment about the amount of concrete that's on top of your head now? Because that lecture room, there's another 4 stories on top of it. And it's sort of, you walk in there and you assume it's safe. Because we've got a good EXA in the country, we've got good training and so on, but you never think before you enter the building and say, but am I happy with what the engineers did over here? You walk in and you continue with your life. And the same with roads. I mean, roads may sound not to be that terrifying, but if you construct a road with inadequate geometry, so the curves are too tight, or you build a road and the materials are not right, and pothole develops and somebody drives through a pothole and have an accident, that's your responsibility to make sure that that is safe. So it's really, it's a career that's highly rewarding. It's really cool to have something that you designed and constructed to see it, but it's a major responsibility on your shoulders, because you say, if I design this bridge over this rail track, I tell you that this bridge will not fall on the train and the cars will fall with it and people will get injured. So yeah, it is a big responsibility.
Wow.
But it's a lot of fun. I must tell you, it's really good to see stuff that you designed and that actually are built, and you realize that it changes people's lives. Even if it's a small road to a small settlement, you can see that people are driving now whereby previously they could not get there with a car. Or make it even more simple. If you've got a community that did not have water, and you do a design for potable water and a pipeline and stuff, and suddenly they've got access to a tap. I mean, that changes people's lives significantly. Again, something that we often tell the medical guys, and I've got family that's medical doctors, so it's not that I say that they are not important, but we always tell them, civil engineers prevent people from becoming ill. Doctors treat them when they are ill already. And the example of that is like in potable water. I mean, we designed the systems to get the water from the river to the dam to the works where you clean the water in a clean pipe to your house. If the engineer stuffed up on that, you can get cholera. Now, yes, the doctor can treat you for cholera, and they are good medicine and so on, but the doctor treats you one by one for cholera. Because I can see one patient, check, you've got cholera, there's your medicine, next one, next one, next one. You as the civil engineer can prevent the whole of the Gauteng region to get cholera because you design a safe system for getting potable water to people's houses. So it's a huge responsibility, but it's really, really deeply rewarding, the stuff that you can do to change people's lives.
I agree. I've actually been reading a lot about smart cities and how inventors like Elon Musk are starting to build these smart cities. And I just think it would be a real scope to start these smart cities in South Africa and throughout Africa.
I think what you said now, Lars, that's the important part. To get New York a smart city is it's nice and cool and stuff, and it's relatively easy because you've got a lot of systems already working. But to get Moketi and Limpopo a smart city, that takes a lot of thinking, and it's not impossible. I mean, if you take the sensor networks that we do for Snoot on our farm, and we take the same electronics that we put in our smart avos and so on, those sensor networks you can install in the shacks in Muketsi and Limpopo to provide you with information on who's got electricity, what's the light level, what's the air quality level, all of that information, making Muketsi a smart city in Africa. And I think that's something that's a major challenge for you guys coming into the system in the next few years, to actually replicate and give even better systems for smart cities and smart transportation in rural areas than in big cities. Because the big city part, it's normally from an economical viewpoint, it's very easy to pay for. And as I say, you've got streets and you've got services, ducts and everything available. So to lift that to a smart city level, yes, it's a big scale, but it's not that much of a challenge. But to go to that small little rural village and do appropriate changes to make that a smart village, those are the cool challenges, because those are the people's lives which you affect much more than the guys in the city that's already got a pretty functional system.
I'm not going to lie, I was big on like going to another country, probably overseas, because we look at their technology and how far advanced it is. And just as an engineer, it would be nice to go and work with that. But just this conversation, it's inspiring to become an engineer and stay here and help better and improve people's lives.
Look, it's never bad. Yes. I know.
Because I feel like it would also be so easy to just go overseas, but South Africa needs us more than overseas does.
That's for sure. And even overseas needs us. Let me explain it to you like this.
There are countries. Yeah.
Yeah, most of myself and my colleagues, and it goes for the other departments also at UP, we do a lot of work internationally. I've done work on this transportation of the tomatoes and stuff in California for about 10 years, where we did not learn from them, we taught them. I've got colleagues at international conferences and workshops. Myself and one of my colleagues are associated professors at 2 universities in China currently, where we do training and teaching with them. They come to us and they ask stuff. Now, I'm not saying it like bragging, wow, we are so clever and so on. That's not the case. But the important thing is to realize that in South Africa, we've got very good pockets of very good knowledge, technology, people that that can make a tremendous difference. I do think it's always good to go and have a look at what happens overseas. And whether it's overseas like in first world or overseas like in worse third world than we are living, no matter. But it changes your perception, and you do pick up different things for sure. I mean, even if we go over there and we teach and we go to conferences and talk to our colleagues, there's always stuff that we pick up from them also, because it's a different environment, it's different materials, it's different traffic and things like that. But I think the real important message that people should get is that we've got very good people in the country, we've got very good educational options, and you can make a major difference both in South Africa and internationally. That's important.
Okay.
Good. So I get a message. Yes.
Sorry, but something I do find very interesting about engineering is how you can go anywhere in the world with it.
Yes, for sure. I mean, it's sometimes sometimes we joke and we say it's one of the bad things for me that the training that my students get allows them to go anywhere, and I always every year I've got students either that finished a few years ago or even students that finished the previous year that get jobs internationally, and they get good jobs. But I think that's also the good thing, that you know that you don't have to feel bad about the people that get stranded over here, that sort of know they stay in South Africa because they cannot get a job anywhere else. That would have been very bad. Currently, I know that the ones that stays in South Africa stays here because they want to stay here and make a difference, and that's important.
I actually love how diverse engineering is, just
Yeah.
as in how it can change, how each engineer can work with each other, and just by grasping one's concept, you can make a difference in another.
For sure, for sure. And I mean, it's always nice. That's where the teamwork is important. That you talk to other people, you learn new things. I mean, one of the things that I've done when I was at CSIR is we developed what we call a luminous road, where we worked with guys that's peer physicists, and we developed a material that you can actually use with your road materials to make sure that they shine at night. And there are currently some of the pedestrian walkways in KwaZulu-Natal that they treat with this type of material to make sure that pedestrians have got some indication at night at where the sidewalks are. And that's totally because we work together with the peer physicists in terms of what they know, what we did not understand at all. They acknowledge that, or they lacked some knowledge that we had, and by combining all of that, you suddenly get to a totally new solution to something that nobody thought about.
Wow.
So you can do cool stuff.
It's also amazing how nature can actually provide some answers that we look for sometimes in engineering. Because I was just doing some research and I found that aerospace engineers are using these what do you call them? These fungus to actually create a shield around these space shuttles because they eat at radiation.
Yeah. Yeah, no, there's cool stuff and that's what's so nice for us to work with the agricultural guys. That's pretty much our neighbors at Engineering 4.0. There's stuff that they understand and know that suddenly when you listen to that, you realize, wow, I never thought about this, but this can change the way that I develop a building. This can change the way that I build a road. because I did not know about this material or this plant or this whatever the case may be. So if you keep your ears and your eyes and your mind open, you can actually make much better use of your knowledge and everything than just to say, no, I'm a civil engineer, I'm only doing this. There's cool stuff that's possible. The term for what you call now is biomimicry. And it's basically saying you mimic what happens in nature.
Prof, if I might add, this is the most engaging Q&A session, I would say. Neck and neck with mechanical engineering.
Thanks, Gilad. It's good to have you over here. Now, these two young ones, I think they must just pass matric this year and skip matric because they are in grade 11 and come and study. I understand enough.
Really? Okay. Interesting.
It's good question.
I'm glad to hear that.
Yeah, no, we had a really nice discussion. I'm quite happy about it.
Fantastic. This is the format that we were thinking of for most of the sessions, for it to be more of a conversation than a lecture from the presenter side. So I'm very glad it transposed into this.
It's good, and I mean it's very appropriate questions and discussions. So I really love it. It's quite good. I'm glad about you guys' time for this afternoon.
Fantastic. And what do the two learners have to say? You guys had a good time so far?
Amazing. I've loved this.
I've definitely learned a lot from this.
Mm.
I'm glad to hear. Unfortunately, we couldn't offer the usual format of EBIT Week this year due to COVID, but we hope that this was still informative enough to answer any questions you might have.
Very informative. I'm just sad that it couldn't be 3 days.
Sorry, Hannah, could you repeat that, please?
I'm sad because the EBIT week is supposed to be like the 3 days, and I'm sad it was only a day. That, you know, this, yeah.
Yes, us too. Us too. We're all looking forward to it quite a bit. It's an interesting experience.
I'm inspired now to.
Ah, sorry.
Oh no! Carry on.
I was just going to say that it's a good opportunity for the learners as well. Even if you find yourself in the engineering program, but you're unsure, a lot of our questions are computer science versus computer engineering. Then even if you've attended the engineering program, there's likely a second-year group leader who's studying computer science, or you'd have other discipline you have questions about. So it's a little bit easier to flow between the disciplines than to have all these Q&A sessions running concurrently. But we make do.
We'll make a plan, yeah. Just so it is possible to still do things in some way.
For sure, Prof.
But I agree with that because I've been wanting to do engineering for quite a while, but I was also unsure whether, you know, there's always second thoughts. Is this what I want to do? And just hearing everything today is very reassuring.
That's fantastic. That's exactly why we do what we do. If all the learners knew what they wanted to study, then we'd be out of a job.
That's for sure.
Yeah.
Okay, guys, anything else from your side? Are you happy?
And
do you have any extra advice? Oh, sorry.
No, it's fine. Say on the same point, for any extra advice, would you say that should I go into civil engineering or something in the built environment? Because I would love to just build stuff that make a difference in people's lives.
In my view, what's happening in the built environment in our setup, it's architecture, quantity surveying, and project economics and so on. If you want to do the actual design of the materials and the bigger picture of not only buildings but pipelines, dams, roads, rail, all of that, that basic science is done in civil engineering. The other guys are extremely important, but for instance, the quantity surveyors in the building sciences, they focus much more on your materials, number of materials, economics, cost, and so on. The architects do the layout design and make sure that it's an appropriate facility, and so, but they don't construct it. So they, and that's why I say they're extremely important. I mean, my architects on Engineering 4.0, I've got huge respect for them because they did things for us that we did not think about at all. But they are not the guys that then say, okay, this is how strong it must be, and this is how you build it, and this is how you actually get it there. So there's a focus for each of them, and even in making a difference in communities' lives. Architects does not only design grand buildings. Architects does things like designing a better hospital, for instance. A good architect can design a better shack for you. And I know that sounds like, man, who designs a shack? But if you've got a good architect, they can tell you, listen, if you are living on that sub-economic housing level, then you need something with this amount of airflow, and this type of window will still be better than anything else. So even a shack can be designed as a better building by a good architect, making a difference in people's lives. And I think it really depends on where your very specific interest is in the bigger area, because in the end, you are going to work together. So it's not something like, no, but if I do civil engineering, I will never be in contact or work with architects, for instance, or with the quantity surveyors or the town and regional planners. We work as teams. It's more a case of where's your very specific interest and the stuff that you really find cool to do and think, but this is how I want to make a difference. That's the focus that you need to have a look out for.
Makes sense.
There we are. Guys, so please, as I said, you can easily get my email address on the website. If you've got more questions or so on, you are welcome to contact. And then we make sure that you get the answers that you need.
Okay.
Would be
Thanks,
a great
Prof.
pleasure.
I think
It
I've
would
got
definitely be. Oh, sorry. Continue.
I think so. You answered more questions than I asked. Like, yeah.
No, that's a
You
real
had more
pleasure.
answers than I had questions.
That's good. The problem is when you sit in my class and I've got more answers than you thought about questions. That's the bad one, because then you write the test. But we try to prepare you for that.
Thank you so much, sir.
It's a pleasure. You guys must have a good long weekend.
Thank you, sir. You too.
Thank you, sir.
Thank you.
You too. And
Appreciate
thank you so much for taking the time out of your day for this.
No, it's a real pleasure. I really enjoyed the discussion. It's always good to chat with young people and listening to you guys' questions and so on. And if you are enthusiastic, it makes our lives worth the while. No, it's a real pleasure. Good stuff. Have a good day there. Gilad, are you guys closing it up, or what's the process?
Yes, we will close it up. I just had a look at some of the other sessions, and almost all of the other disciplines have closed, including mechanical.
Okay.
So you've won the conversation race.
That's good. I had two very good guys with me.
Yeah, I'm not sure if industrial is still online. No, I see it closed as well. Okay.
Yeah, no.
And I believe that's it.
Shows them we are civil. We've got a civil way of dealing with people.
There we go.
Thanks very much, Prof. Wynand. I really appreciate and keeping everything together and your passion for what you are doing and what you believe in. I think I see with all the other lecturers as well, they just speak from the heart, and the questions that the students are asking are just amazing. And it's the real life questions that they're asking, and I think that is what I see today online is that they actually can share those personal discussions so that they can hear and see and feel how you feel about your discipline. But the other thing that I also picked up is the way that everybody is referring to other disciplines, and that is amazing. So the students can see it's not isolation on an island. We all, to some extent, have a connection with each other, the departments. That's great. Thanks very much, Prof.
It's a real pleasure. Thanks for you guys for doing all the groundwork and the background work and so on. That was really amazing, and I think it worked very well.
Thanks, Gilad, for you as well.
Thank you.
Bye-bye.
Thank you, guys. Bye-bye. Have a good weekend.
Bye-bye, Hannah.
Bye. Thank you, everyone, for making this happen.
It's a great
That's
pleasure.
a pleasure, Hannah. It's nice having you online. And I assume you're in matric, so good luck with your final year exam if you are in matric.
Grade 11, but I really do appreciate it. Thank you.
Yeah, so you've got a rough time ahead of you as well. So we really salute your students for hanging in there. And we are of the opinion that you guys are going to be another type of generation that you are going to fly when you come to university, because you are actually learned in a very short space of time how to operate online. And you will be well prepared for university in 2 years. Okay, Hannah, see you around. Bye.
Bye. Thank you so much. Bye.